Hey guys, today we're going to look at algebraic properties of limits. Some of them are pretty common sense, and then when we get over to composite limits, those are way less common sense. At least they were for me. So bear with me as I try to explain it to the best of my abilities. But let's go through these ones first. Properties of limits. Basically, you can find limits even if you don't have equations to work with, because there are some certain properties that apply. So if, for example, you have the limit of two functions being added or subtracted together as x approaches c, what you can do is you can take their limits separately and add or subtract them. Now, provided that for all of these, your limits have to exist first. So like, for example, if the limit of g of x was did not exist, was d and e, then we couldn't find d and e added to some number, right? So this is the provision that has to be true in order for these properties to work. Limits of a property, limit of a product. So if you have two functions being multiplied together, you can multiply their limits together. Limit of a monomial, you don't really have to worry about because it's just direct substitution. So the limit of a times x to the n as x approaches c. Basically, all you do is you plug in c, but that's what we do for limits anyway, starting off. Limit of a power or a root basically means you can apply that power to the whole limit or the root to the whole limit instead of just the function itself. And then limit of a quotient as x approaches c. If you have two functions being divided inside of a limit, you can do the division of their limits separately, provided that your denominator limit is not equal to 0, because we can't divide by 0. All right, let's go look at some of these guys. The first thing we're going to do, as suggested by my Facebook AP Calculus group, is we're just going to cross this off. And we are going to write ourselves a couple little notes here. So with composite functions, we have to work from the inside out. And we have to test your left-hand limit and your right-hand limit. Test both of them. Okay. All right, and for the problems that are below, what we're actually going to do is we're going to start with number 2. I know it seems weird, but for number 2, it's just a nice, easy example of a composite function one. So it's going to be great. All right, so we are going to start working from the inside out with this guy, and we'll have to go back up to the graphs in a second, but basically it's a composite function because I have f of g of x. So the first thing I'm going to do is I'm going to split that up into its left-hand limit and its right-hand limit. G of x as x approaches 2 from the left, and then f of g of x as x approaches 2 from the right. Okay, so now we're going to start working from the inside out. So I'm going to look at g of x, and as x approaches 2 from the left-hand side, I'm going to look at what happens to my function of g. Excuse me. So on my graph of g of x, as I approach 2 from the left-hand side, it looks like my function is going to a positive 1. So as I approach 2 from the left-hand side, it looks like my function is going to 1, but it's coming at 1 from values that are less than 1. So as I approach 2 from the left-hand side, g of x is approaching 1 from values that are less than 1. So you could say g of x is approaching 1 from the left-hand side as well. So basically, this is going to change into the limit of f of x as x approaches 1 from the left-hand side. Because I figured out as g of x, as my x value approached 2 from the left-hand side, this function started approaching 1 from values less than 1. So as I approached 2 from the left-hand side, my function itself started approaching y values that were getting closer and closer to 1, but were less than 1. So I'm essentially replacing my inside function with a new variable, and what the answer to, as my x values inside of g approach 2 from the left-hand side, what was the answer to that particular limit is now what my x value is approaching. It's a nice substitution method. And then I can do the same thing from the right-hand side. So as I approach g of x from the right-hand side as I approach 2, it looks like my function is approaching values of -1, but it's approaching values of -1 from above, basically. So it's approaching values of -1 from values that are greater than -1. So I am, again, replacing my g of x with a new variable, with x. And the answer to that question is, as my g of x approached 2 from the right-hand side, I approached -1 from the above side, or the right-hand side. All right. And so then now you can treat this like a normal problem because you're just looking at one graph now. So limit of f of x as x approaches 1 from the left-hand side. So here's f of x. So as I approach 1 from the left-hand side, I get 4. And then for my second limit, it says limit of f of x as x approaches -1 from the right-hand side. So I approach -1 from the right-hand side. I also get 4. So the answer to this question is 4. Yeah, it's a little bit counterintuitive and it's a little tricky because you're doing a little bit of weird substitution in here. If it makes you feel better to use a different variable here, you could feel free to use like a u or something like that, and then have u approaching some value so that way you don't get mixed up with the x's from this problem in this problem. But we're just so used to using x, so that's also an option. All right, we're going to go ahead and do number 3 now, which again is going to seem counterintuitive, but then we'll go back and do one. This just has a lot of things going on, so I wanted to work on the single compositions first. All right, so again, you have a composition of functions because I have 2 minus x squared inside of g. So I'm going to go ahead and split that up into its left and right hand limits, and then I'm going to do some substitution. Sorry, I lost my train of thought there. So from the left-hand side of g of 2x squared, and from the right-hand side, okay, for this guy, we don't actually have a graph to look at for 2 minus x squared. So as I am plugging in numbers that are closer and closer to 0 but less than 0, so like for example, if I'm plugging in negative 0.01, basically what's going to happen is as this gets closer and closer to 0, the 2 minus 0 is going to get closer and closer to 2, but from the left-hand side, because it will technically always be smaller than 2, no matter how close to 0 you get. So like, for example, if I did 2 minus 0.1, like that gives me 1.9. And if I did 2 minus 0.01, that gives me 1.09. And then 2 minus 0.001, that gives me, 1.009, right? So I'm getting closer and closer to 2, but I'm always going to be less than 2. So when I do my replacement here, when I do my substitution, what my limit will now be approaching is it will be approaching 2, but it will always be from values less than 2. And so then I can write g of x that way. And the same thing's actually going to happen down here, regardless of whether or not I'm plugging in negative numbers really close to 0 or positive numbers really close to 0. When I square them, they'll always turn positive, and so it'll always end up with 2 minus 0.1, 2 minus 0.01, 2 minus 0.001. So again, I'm going to be finding, as I replace that with an x, as I plug in numbers closer and closer to 0 but greater than 0, I'm still going to be approaching 2, but it's always going to be from the left-hand side. And so then what that actually tells me is that these answers will automatically be the same as long as this limit exists. All right. So if I go to g of x and I say what's happening as I approach 2 from the left-hand side, my answer on g of x looks like it'll be 1. Woohoo! All right. Last but not least, the first problem. Seems, again, backwards, but So first and foremost, we can break this up because I have a product going on. So I'm going to go ahead and I'm just going to over here off to the side break it up into the two things I'll be finding because I want more space down here still. So limit of f of x as x approaches 1 will be one of my things that I'll be finding. And then I'll multiply it by the limit of g of x plus 1 as x approaches 1. Okay, and then this is a composite function because I have an x plus 1 inside of g. So I'm going to go ahead and split that part up into its left-hand and right-hand limits down here. So limit of g of x plus 1. Oops, it's very messy. As x approaches 1 from the left-hand side, and then limit of g of x plus 1 as x approaches 1 from the right-hand side. All right, so as as I approach 1 from values that are less than 1, I'm going to be plugging in like 0 0.9, 0 0.999, 0 0.99999. And so then this will turn into, it gets very close to 2, but it will always be less than 2. Right? If I plug in 0.999 plus 1, that would give me 1.999, which would be close to 2, but less than 2. And then if I'm plugging in numbers, substitute that in now, that are close to 1, but from the right-hand side, so like 1.1, 1.0001, I'm going to be approaching 2, but it's going to be from numbers that are always going to be technically greater than 2, because as I plug in values close to 1 but bigger than 1, the x plus 1 will turn into a number slightly greater than 2, always. So then we have to look at the left-hand and right-hand limits here. So on g of x, as I approach 2 from the left-hand side, I get 1. And as I approach 2 from the right-hand side, I get negative 1. And then now we come into our first example where because these don't match, right? Here they match, so I got 4. Here they matched automatically because they're the same limit, and I got 1. Up here, this part, oops, does not exist. And so I can't do this product thing because this part doesn't exist. So I can't do the product of two limits when one of your limits doesn't exist. So that's the final answer for that one.